Hello, and welcome back to another episode with It's Dr. Dan, and today we're going to dive further into the introduction to nuclear chemistry, specifically looking at a half-life. So what this is all about is going off of what our last video was all about, which was all the different types of nuclear radiation. So whenever you have an unstable nuclei, let's say like the one here with all these little protons and neutrons, it will decay, meaning it could go through, let's say, a gamma ray radiation where it just releases energy. Maybe it releases a positron, a beta particle, an alpha particle. So if you're interested in balancing those reactions, refer to my other video. This one's just on half-life. So when we have radioactive decay, what exactly is happening? Well, it takes so much time for each one of these radioisotopes to decay and break down. Now, every time, whenever we have one of these, it goes through a half-life. So what the whole idea of a half-life is whenever we have a radioisotope, and it's the time it takes for it to decay by exactly 1/2 of its original amount. Meaning that if I have, let's say, a sample here, and it goes through exactly 1 half-life, so we'll just say 1T 1/2. So when that happens, it's going to decay by half. So like as we have on this original portion here, this is 100%. Then when it goes through 1 half-life, it's going to go down to 50%. If it goes through a second half-life, it will have 25% remaining, and that will keep going down over time. It'll keep decreasing as we move further and further and further, decaying by half. So what kind of problems could you possibly see? Let's go through a bunch of different calculations to show how this is going to happen. And we'll even look at what kind of ranges of values we'll even see for what to expect when it comes to working with half-lives. Let's take a look. The first thing is, what about the ranges? So half-life values can range from all kinds of things from minutes to years to sometimes millions and billions of years, depending on the actual radioactive process and how stable or unstable the element is. Here I just included about 4 different examples that we have here, ranging from carbon-14, which we use to date historical artifacts that we find around the world, to things that could be used more in medical applications where they last on shorter timescales. So one thing you might notice is that they all have different processes, such as beta particles, alpha particles, positrons, where they could last everywhere from thousands of years to as short as just a few minutes. So we're going to be talking about all kinds of different scales and just adding up the values. So this is for introductory chemistry, so we're not going to be going through the exponential equations that you'll see in things that are more general chemistry 1 or general chemistry 2 with kinetics. This is just introductory level examples. Let's go into the different problems. With our first example, what we have here is a 20 milligram sample of iodine 131 decays, and it only leaves 2.5 milligrams. How long would this take? So how exactly are we going to go through this? Well, the first thing is we have to remember is that every time we go through a half-life, the mass or the amount is going to decrease by half. So there are a lot of different little strategies that we can go through for how to do this. But we have to remember is that our original sample is starting at 20 milligrams. And what we are going to be doing is dividing it by half for every single half-life. So being that we're going from 20 to 2.5, let's first just divide our masses in half. So our first one would go from 20 to 10. Our second one would go from 10 to 5, right? 10 divided by 2 is 5. Then if we take 5 divided by 2, we will get to 2.5. So how much time exactly passed? Well, let's take a look. Every single one of these arrows represents a half-life. So it's in a certain amount of time that is passing. So in this particular problem, a half-life is equal to 8 days. So what exactly occurred? Well, after the first half-life that is here, this was 8 days exactly, which as the course of time took place, it went from 100% of our sample and decayed it down to 50% across the course of one single half-life. Now, once we went to the second half-life, which was another 8 days, so a total of 16, it went from 10 to 5, meaning that we now have 25% of our original sample remaining. Now, when we go through our last and final half-life, we are down to 12.5%, which means that this took a total of 24 days for this to break down, to decompose, and go through this beta decay process. So these are some of the ways you can map it out. You don't have to do all the percents and all the work all the time, but it just helps to be able to visualize and see it. Let's go take a look at some more examples. If you start with 100 grams of radon, how much sample would be left after 44 days? So, and in this problem, I also give you exactly how long the individual half-life is. So we can see that we have a half-life of 11 days. So what we need to do is map out exactly how long would this take. So this one, it could be, you could do it a slightly different way. Well, how many half-lives would fit into 44 days? Well, we can kind of do a little bit of math here. If we have 44 days total, and I divide that by 11 days, it's going to be about 4 half-lives is how long this is going to take. So let's show how that would work, right? I would first start once again at 100 grams. Across the first half-life, it would go down to 50 grams. The second half-life would go down to 25 grams. The third half-life would go down to 12.5 grams. And then the fourth half-life would go down to 6.25 grams. Now to show our work here, we can put down our T halves to just show that each time this decayed, this would be changing. So every time that this happens, this is going to be going from radon and transforming into a new element as a result. And then we can see that it's going to be releasing alpha particles every single time that this is happening. So it's going to be changing. So this is how much is decaying. So at the end, you're only going to have about 6.25% of your 100 gram sample that is remaining. So let's take a look at some other different types of problems that we could see when we do these. If we have a sample of 3,1 hydrogen, so hydrogen 3, and that's decaying through beta decay, and it only leaves 3.1% of the original sample, how long would this take? The half-life for this one is 12.3 years. So how long? How can we do it? Well, with this one, we didn't get a starting amount, but we were given a percent. So if we know that every half-life decays by half, why don't we just map out the percents, right? Just like how we did in the very beginning of this video. So if we have 100%, it would decay down to 50%, which would then decay down to 25%, which would then go down to 12.5%. And that would further decay down to 6.25%, which would then go down to 3.125%, which is approximately where we want to go. So how many times will this change? Well, we can number it out, right? We have 1, 2, 3, 4, 5 half-lives that this will have to go through in order for 3,1 hydrogen to fully decay. So all we need to do is take our half-life value, right, which is 12.3 years, and we would multiply that by 5, and we would end up with our final answer for this particular problem, which would be 61.5 years is how long this would take for it to fully go down to only 3% remaining in this particular problem. So let's take a look at another example. So you start with 200 milligrams of thallium-207. So after 100 minutes, there is only 12.5 milligrams left of your sample. What is the half-life of this decay process? So how can we try to figure it out? Well, we were given how much time there was, and we also have the starting and the end masses of this particular problem. So why don't we try to map out how much we would have? So the first thing what we would do is we are starting with 200 milligrams, and we are going to be dividing that mass every single time it goes through a half-life calculation. So go from 200 to 100 would be the first one. Then on the next one, we would go from 100 to 50. Then when we divide it again, we're going to go from 50 to 25. And then when we go one more time, we're going to go from 25 to 12.5. So we are just dividing that in half with each iteration. Now, how much is our half-life? How do we do this? Well, if you can see, we have 1, 2, 3, 4 individual half-life intervals. We know that there was 100 minutes that passed. So how would we figure out the half-life? Well, we're just going to divide it by the number of intervals. So 100 divided by 4. And what that's going to tell you is our half-life, which in this case is 25 minutes, is one half-life for this particular reaction. Now, if this were to kind of keep going over and over and over again, you could keep showing how far this could truly decay during that time period. It could keep going. Now, with half-lives, this is the general idea for most of these expressions, being that as they decay, they're going to continuously keep approaching 0% over time. So you can see this keeps dividing and dividing and dividing. Generally, the rule of thumb is eventually it will get down to just one particle left or one little amount left, and it will decay to nothing. It usually takes about 10 cycles or 10 half-lives for that to happen, for it to be over 99% gone. You will see that you can continue dividing it by 2 as long as you want. But this is how radioactive processes work. They take time. They're unstable. They're metastable, right? So as it goes to that radioactive decay, we will see them continuously break apart, transform into new daughter nuclei as it goes. I hope that it helped by showing how to do these calculations, and I hope that it helps you do future homeworks and to better further your understanding, whether it's in introductory chemistry and nursing and radiation technology, to keep furthering your understanding. Thank you so much for listening, and I hope that this video helped. Please hit that like and subscribe button if it did, and I hope to see you around for future videos. Bye now.